In the previous video, from this experimental observation, we have noted that the influence of strain rate is significant, right? And the strain rate is not the only significant effect, but also the temperature, right? And in this video, that's what we are going to discuss. So in this video, we are going to discuss about the effect of temperature on flow properties. Okay, so directly we'll go to some experimental data. If you see the stress strain curve, this is the stress strain curve. The stress strain curve for some material which is mild steel at minus 196 degrees centigrade, the material acts like a brittle material. So no necking, so no coming down or anything. Okay, but when I rise the temperature, then it becomes like kind of ductile material, and when I rise the temperature further, I was able to observe a stress strain curve like this. Okay, and in this, from this picture, we can observe one thing, which is the change in yield strength with respect to the temperature. If you see, the yield strength is actually decreasing. Okay, and it's been observed that the decrease for different material is observed to be kind of exponential decay, something like that. Okay, and then this is the reduction of area. Okay, this we can't identify from the stress strain curve, but from the reduction of area. Okay, and if we observe that at very low temperature, the reduction of area is almost zero, which means it's acting more like a brittle material, but at an elevated temperature it acts like ductile material. Okay, so therefore there is a increase in the reduction of area. Okay, so now how can I write in an equation form what is the effect of temperature in stress? Okay, that's what we're going to see. And from this curve, as I mentioned earlier, it shows something like a exponential decay. So people have come up with a relation, which is this relation. Okay, so for a constant strain and strain rate, okay, the influence of temperature on the flow, the yield stress is given by this equation. Okay, where Q is known as an activation energy, and for two different temperature, if I know what is sigma for each temperature at constant epsilon and epsilon dot, okay, from that we'll be able to calculate what is Q and what is C2, because this R is just a universal gas constant. Okay, and to calculate Q, for example, if sigma 1 is given for a corresponding T1 and sigma 2 is given for a corresponding T2, from those information we'll be able to calculate Q using this formula. Okay, so once I calculate, it's very easy to calculate C2. All I have to do is either I have to put T1 over here and sigma 1 over here, or T2 over here and sigma 2 over here. Okay, so by doing that we'll be able to calculate what is C2. Okay, so that's how we can introduce the influence of temperature in the yield strength. Okay, fine. Now we are going to see how the instability of the material is changing. By instability, we're going to see how the ultimate tensile strength is changing with respect to temperature. Okay, so we know that P is equal to sigma A, and sigma is not just a function of strain, okay, as we discussed in power law and all those things, but also from the previous video and this video we have observed that it also a function of strain rate as well as the temperature. Okay, so therefore what I can say is d sigma by d epsilon is equal to dou sigma by dou epsilon plus dou sigma by dou t into dt by d epsilon plus dou sigma by dou epsilon dot into d epsilon dot by d epsilon. Okay, so now if I from this relation I'll be able to write this one, which is equal to minus sigma plus d sigma by d epsilon, and in the place of d sigma by d epsilon I could put this one. So finally dp, okay, for dp what do I get is this relation. Okay, so this is the relation I'll get for dp, and for instability the condition is dp is equal to 0, which means this whatever the thing inside the bracket, that has to be 0. Okay, so if that has to be 0, then what I can say, for example for an adiabatic heating, okay, for an adiabatic heating what I can say, so according to the first law of thermodynamics, Q is equal to delta U plus W, right? Energy, sorry, work supplied, sorry, work came out of the system. Now if we see the increase in the internal energy is given by C, the heat capacity, rho density, into a slight rise in temperature. So C rho into dt is the increase in the internal energy, and work is sigma into d epsilon, that's the work supplied to the system. Okay, and so therefore I can write dt by d epsilon is equal to sigma by rho cp. Okay, and now what I can do is in the place of dt by d epsilon, which is over here, I could write sigma by rho c. Okay, and then if in case the influence of strain rate is not much, because we have observed that at low temperature the influence of strain rate isn't that much, only at an elevated temperature the influence is considerable. So at low temperature under an adiabatic condition, okay, what I can say is dou sigma by dou epsilon minus sigma is less than or equal to this quantity. Okay, so if there is a rise in temperature, okay, if there is a rise in temperature, okay, if there is no change in temperature, then what I can say is dou sigma by dou epsilon minus sigma should be equal to 0 for instability. Okay, but if there is a temperature influence, then this will come into the picture. Okay, this will come into the picture, and at instability this is equal to sorry, this term is equal to this term. Okay, so therefore we observe that the ultimate tensile strength will be changing. Okay, so we observe that the ultimate tensile strength is will give us this quantity to 0, but if there is a rise in temperature, this quantity is not equal to 0 but equal to this at instability. Okay, so if I rise the temperature, then there will be, from this relation I can say that there will be a drop in the ultimate tensile strength. So that's what we observe in this picture. So the ultimate tensile strength is decreasing when I raise the temperature. Okay, so that's the influence of temperature in the stress strain curve. Thank you.